Okay, hello everyone in a new video. So I have reached part 3 of chapter 7, which is the chapter of the voltage of the mains in the second unit of electricity. Then in this one we are going to solve some exercises. Then let's start by exercise number 1, section 12. Why it is essential, so here essential means important, to distinguish between the live and the neutral terminals. Now because we know that the live terminal is dangerous and causes electrocution. And number 2, describe how one can distinguish between them using a screwdriver tester. Which is the live main indicator. Now the second exercise, they are telling me domestic installation consists of a TV of 800 watts, an iron of 2000 watts, an electric heater of 3500 watts, and 2 lamps. Each of the lamps is given by 70 watts. All are functioning normally under an effective voltage of 220 volts. So here we have the effective voltage is equal to 220 volts. They are asking me what is the most convenient circuit breaker for such an installation. And here, in order to know the most convenient circuit breaker, first we need to determine the main current that is traversing this domestic installation, and we know that in this case they are connected in parallel. Then for this reason all of them are functioning normally under an effective voltage or an applied voltage of 120 volts. Then let's start by calculating the total power, because we know that if you want to determine the current, P is equal to U multiplied by I. So in order to determine I, we need to know U and P. Then P total, which is equal to the P of the TV plus P of the iron plus P of the electric heater plus P of the lamp plus P of the lamp. So here I have placed two values for P of L because we have 2 lamps. So the power of the TV is given by 800, the power of the iron is given by 2000, the power of the electric heater is given by 3500, and the power of each lamp is given by 70. So notice that all of these are expressed in watts. So the final answer, which is the sum, is given by 4180 watts. Then the total power of this domestic installation or consumed by this installation is given by 4180 watts. Now after we have determined P total, we know that P total is related to the main current because U effective multiplied by I main, and we are interested in determining I main. Covering I with our hand, then I is given by P divided by U, which is equal to 4180 divided by the effective voltage given by 220. And in this case, so here, sorry, I have done a mistake. Now this is not given by 4180. Let me double check the calculation. So we have 800 plus 2000 plus 3500 plus 70 plus 70. Then this is given by 6440. So the total power is given by 6,440 watts. Now this is divided by 220, so it is equal to 29.27, because all of these are expressed in the SI P and U, so the value of I main will be in the SI, which is amperes. So in this case, the main current traversing the circuit is given by 29.27 amperes. So now yet we didn't answer the question, which is what is the most convenient circuit breaker. Then let's refer to the definition of the convenient circuit breaker, which is given by the most convenient circuit breaker is the one having rated current slightly greater than the main current, so here we don't have any choices of referring to the values of the rated current. We know, knowing that 29.27 is the main current, so simply a circuit breaker carrying the indication 30 amperes would be suitable for this domestic installation, because we know that what does this indication represent. This is the rated current under which the circuit breaker protects this domestic installation. Now moving to exercise number 3, they are telling me a domestic installation is fed by an alternating sinusoidal voltage of effective value 220 volts. This installation includes the following electric appliances connected in parallel. So we have the electric oven, the iron, the heater, and two identical lamps acting as ohmic conductors. So what is meant by ohmic conductor? We can apply Ohm's law of resistances R is equal to 880 ohms. Number 1, they are telling me show that the electric power consumed by each lamp is given by 55 watts. So here the effective value is given by 220 volts. And we are interested in determining the power of each lamp. So the power is usually given by the first form, which is given by P is equal to U multiplied by I. But notice that in this case, we don't have the value of the main current traversing the lamp, and we are interested in determining the power. However, we have the resistance. So knowing the resistance and knowing the voltage, we know that the power is given by either P is equal to U multiplied by I, P is equal to Ri squared, or even P is equal to U squared divided by R. Now, knowing the voltage and knowing the resistance, we know that we are interested in this form, but the thing is that we cannot use this unless we prove it, so we are interested in proving P is equal to U squared divided by R, starting from this form. So if you compare both forms, so because R appears, it means that we need to start with the general form and apply Ohm's law, which is given by U is equal to R multiplied by I. Now comparing both forms, it means that we need to get rid of I, because I doesn't appear in this form. So I is given by U divided by R. Now replacing this one here, so we have that it is equal to U multiplied by U divided by R, which is equal to U over 1 multiplied by U divided by R, which is equal to U squared divided by R. So the power is given by U squared divided by R. Now P, which is equal to U squared divided by R, we are calculating P of the lamp, which has an applied voltage 220, divided by, so this is raised to the power 2, divided by the value of R, which is given by 880. Plugging this on the calculator, then the value of the electric power is given by 55. Since both U and R are expressed in the SI, so the value of P will be in the SI, which is what? So the power of each lamp connected in this domestic installation is given by 555 watts. Now in number 2 they are telling me determine in kilowatt hour the electric energy. The formula of the electric energy is always given by E is equal to P multiplied by T. Now we know that the SI unit of electric energy is joules, but here they specified kilowatt hour consumed by each lamp when it functions normally for 20 hours. Now since the specified unit of energy is kilowatt hour, and can be decomposed into kilowatts multiplied by hour, which means that the power must be expressed in kilowatts and the time in hour. So before starting with this formula, let me write here that the power of each lamp is equal to 55 watts. And knowing that since we are interested in converting from watts to kilowatts, we divide by 1000. Then 55 divided by 1000, which is equal to 0.055 kilowatts. So the power of the lamp in kilowatts is given by 0.055 kilowatts. So the electric energy of the lamp is given by P of the lamp multiplied by T, which is equal to 0.055 multiplied by 20. Plugging this on the calculator, so here L stands for the lamp, and it's not important to write the subscript L. We can remove it, for example. So it's given by 1.1. Since this is expressed in kilowatts and this is in hours, so the unit of the consumed energy in 20 hours is given by E is equal to 1.1 kilowatt hours. Now in number 3, all the appliances function normally at the same time. 3.1. Calculate the total electric power consumed by this installation, and by the total it means the sum. So this installation consists of these appliances. So P of the electric oven plus P of the iron plus P of the heater plus P of the lamp plus P of the lamp, which is equal to 2000 plus 1000 plus 10,070 plus 55, and here the power of the lamp, since all of these are expressed in watts, so the power of the lamp must be replaced in watts and not kilowatts, because we know that in physics whenever we are adding quantities, all of them must carry the same unit. Now the sum of these numbers is given by 4180, and because all of them are expressed in watts, so this is watts. So P total is equal to 4180 watts. Now in 3.2, deduce the main current I, and by deduce it means that we need to use the previous part. In the previous part we have determined the total electric power, and you already know that the effective voltage is given by that. So P total is equal to the effective voltage multiplied by the main current, which is denoted by I. Then constructing the triangle, setting up the triangle and covering I with our hand, so it's given by P divided by U. I is denoted by I, P total over U effective. So 4180 divided by U effective, which is given by 220. This is equal to 19, since both P and U are expressed in the SI, so the value of I will be in the SI, which is amperes. Then the main current traversing this circuit is given by 19 amperes. Now in 3.3 they are telling us consider the 3 circuit breakers carrying the inscriptions 15 amperes, 20 amperes, 25 amperes. So what does each of these inscriptions mean? They represent the rated current under which the circuit breaker protects the domestic installation. Now they are asking me which one is the most convenient one for this installation. Then let's write the most convenient circuit breaker is the one having rated current slightly greater than the main current. So the main current is given by 19. The rated currents greater than 19 are given by 20 and 25. 15 is eliminated. But the one which is slightly greater than 19 is given by 20 amperes. 25 amperes can work for this domestic installation, but this is more convenient. So in this case, it's given by 20 amperes. Now moving to the next exercise, which is exercise number 4. They are telling me document 1 represents a wall outlet of the mains for which the effective voltage is 220 volts. Indicate for each of the following statements if it is true or false. Correct the false statement. So this is the first time that we solve such type of exercises in the second unit. Now, whenever we want to correct a statement, first of all, we need to do a justification. So we always start by the justification. Then whether it's true or false. Then we correct the statement. Now, sometimes if the statement is true, we cannot justify, but we will always try to justify. And the important thing is that we need to rewrite the statement correctly. So whenever it applies, we need to answer in the following form, and each form has a certain mark. Now let's start by number 1. They are telling us to distinguish between the live and the neutral terminals. We use a tester, and this is true. So here no justification can be applied because the tester or the screwdriver tester or the live main indicator is an instrument that is used to distinguish between the live and the neutral terminals. So the first statement is true. As for the second statement, they are telling us a voltmeter adjusted on AC mode and connected across the ground and the neutral terminals display 220 volts. So we know that the voltmeter measures the effective voltage, but at least one of the terminals must be connected to the live because the live is the one responsible for the electricity. So in this case, the statement is false. So here we cannot justify, so no justification applies, but we need to rewrite the statement correctly. We say that a voltmeter so we will change the ground to the live, or you can even change the neutral to the live, connected across the live and the neutral terminals. Displays 220 volts, which is the effective voltage. Now in number 3, they are telling us the voltage delivered by the wall outlet is alternating triangular. So we know that this is false and it is sinusoidal. Here no justification applies. So let me say false. The voltage delivered by the wall outlet is alternating sinusoidal. Now in number 4, the maximum voltage of the mains is given by U maximum is 220 over square root 2 of 220 over square root 2. So here there is typo, this volts must be upward. So knowing the effective voltage, we are interested in determining the maximum voltage. So here we can first start by the justification, which is the calculation. Let me make some space above. So we know that the effective voltage is equal to UM divided by square root of 2, and we are interested in determining the square root of M. Then constructing the triangle here, because we have divide, then U effective will be at the bottom, UM here, and square root 2. We are interested in determining UM, so covering UM, then UM is given by U effective multiplied by square root of 2, and we know that the value of the effective voltage is given by 220. And because the effective voltage is expressed in volts, so this is expressed in volts. And here this is multiplied. So notice that the expression of the maximum voltage is wrong, so the statement is false. And now let's rewrite it correctly. The maximum voltage, or the maximum value of the voltage of the mains, is UM is equal to 220 square root of 2 multiplied by V, or 220 square root voltage. So this is it for exercise number 4. Now exercise number 5, which is the last exercise in this video. So in order to show evidence of the role of a fuse, we construct the circuit of document 1. This circuit includes in series a generator G delivering across its terminal a constant voltage UPN is equal to U is equal to 24 volts. So the trick in solving such type of exercise is to write the voltage on the electric circuit itself as well as the traverse current. Now here they didn't represent the symbol of the generator, but since they are telling us a constant voltage, so it is a DC voltage, and because Pn is positive, the voltage measured from P to N, which means that this is the positive pole and this is the negative pole, so this is similar to this symbol. Okay, so in this case the current will be traversing from this pole and entering back to this pole like this. Okay, now we have two identical lamps L1 and L2. Carrying the indications, each of them carry the indications 12 volts, 0.6 amperes. A fuse F of negligible resistance carrying the following indication. Now in 1.1, give the significance of each indications carried by the lamps. They are talking about the indications of the lamp. Let's start by 12 volts. We know that this is the rated voltage. Of the lamps L1 and L2, under which they function normally. Now as for 0.6 amperes, we know that this is the rated current. Under which they function normally. And here I'm, in order not to write for each lamp two statements, so this is a 12 volts is for both lamps L1 and L2 as well as for 0.6 amperes. Now in 1.2 they are telling me determine the resistance of each of the two lamps. So we will determine the resistance of one of the lamps, and because they are identical, both lamps will have the same resistance. And we know that the resistance of the lamp can be determined using Ohm's law. Although here we don't know if the lamp L is functioning normally, but we can use the indications simply because we are calculating resistance. So apply Ohm's law to L1. Ohm's law is given by U is equal to R multiplied by I. We are interested in determining the value of R. Constructing the triangle, putting our hand over R, then R1 is equal to U1 divided by I1, say for example, and 12 divided by 0.6. So plugging this on the calculator, then the value of the resistance is given by 20. Since both U and I are expressed in the SI, so the value of R will be in the SI, which is ohms. So R1 is equal to 20 ohms. Similarly for L2, so in this case R2 is also equal to 20 ohms. And this resistance is for both L1 and L2. Now in 2.1 they are telling me the voltage across F is 0, so notice that the fuse is of negligible resistance. So the voltage is 0 since it is of negligible resistance. So in this case we have that UPA is equal to 0. So I'm measuring the voltage as in the direction of the current from P to A, okay? Now in 2.2 we need to determine the voltages U1 and U2 across the terminals of L1 and L2 respectively. So we need to determine the voltage across the lamp L1, which is given by UAB, which is equal to U1, and the voltage across the lamp L2, which is given by UBC, which is equal to U2. Now we know that the law of addition of voltages, it will yield to a linear equation and one unknown. In this case we have two unknowns, UAB and UBC, but using the fact that the two lamps are identical, it's sufficient to determine the voltage UAC, prove it is equal to 24. Then we will divide the voltage by 2, which is equal to UAB and UBC because they are identical lamps. So first, as a first step, let's determine the voltage UAC across the terminals of the lamp. And here I have specified that we are interested in determining UAC because UAC must appear explicitly in the equation. After we determine UAC, we will divide it by 2 to determine UAB and UBC. So let's say apply law of addition of voltages. So always on the left we write the voltage of the battery, which is given by UPN, measured from the positive pole to the negative pole. And on the right hand side of this equation we'll go from P to N across different electric components, making sure that UAC must appear. So from P to A, from A directly to C, from C back to N, and we are interested in determining UAC. Now UPN is equal to 24, UPA is 0 justified, UAC will be kept as a variable, and across C and then we have wire, and we didn't justify this previously, that UCN is equal to 0, and the reason is given by connecting wire. So what's the type of this equation? This is a linear equation in one unknown. The unknown is UAC. So in this case, UAC is equal to 24 volts. But notice that here we are talking about the voltages across the lamps U1 and U2. So let's say since the lamps L1 and L2 are identical, then they have the same voltage, which means that the voltage UAB of the lamp L1 is equal to the voltage UBC of the lamp L2. Now notice that in this equation, B will cancel out and we are left with the voltage UAC divided by the number of lamps we have, which is given by 2, which is equal to 24 divided by 2, which is equal to 12. Since UAC is expressed in volts, so the voltages UAB and UBC will be in volts. Let me complete it here. So in this case, U1, which is equal to the voltage UAB, is equal to 12 volts, and U2, which is equal to the voltage UBC, is equal to 12 volts as well. So this is 12 volts and 12 volts. Now in 2.4 they are telling me what is done. 2.3. They are telling me deduce that the lamps function normally, and whenever we want to discuss the functioning of the lamp, we need to compare the applied or traverse to the rated. In this case, we have the applied voltage, and notice that in this case, the applied voltage is equal to the rated voltage of the lamp. So because they are in series, they will be traversed by the same current I. So let's discuss only current across the lamp L1, and this is a series grouping circuit, so the current is the same. Let's say since the applied voltage is equal to the rated voltage of the lamp L, so we are talking about the lamp L1, or you can discuss the lamp L2. 12 volts is equal to 12 volts. Then the lamp L1 functions normally. So, and in this case, because the lamp L1 is functioning normally, the traverse current will be directly equal to 0.6 amperes, which is the rated current. Now, moreover, in 2.4, they are telling us what is then the value of the current I through the circuit. So here, they are talking about the lamps L1 and L2. I have only discussed the normal functioning of the lamp L1. So let me say similarly for L2. Okay, now in 2.4, what is then the value of the current I through the circuit? So let me say since the lamp L1 is functioning normally, then the value of the traverse current is equal to the rated current of the lamp L1. So in this case, the 0.6 amperes is equal, so I is equal to 0.6 amperes. Okay. So since the lamp L1 is functioning normally, then the value of the traverse current is equal to the rated current of the lamp L1. So we have that I is equal to 0.6 amperes. Okay. Now notice that here in this case the fuse has a rated current which is 0.65 amperes and the traverse current is 0.6 amperes, which is less than the rated current of the fuse, so the fuse will not burn out. So always whenever we have a fuse in an electric circuit, we should keep an eye on the comparing the value of the traverse current to the rated current of the fuse. Now in number 3 they are telling me the lamp L1 is short circuited. So by short circuiting the lamp L1, it means that its voltage will be 0, because we know that whenever an electric component is short circuited, then its voltage is 0. What is meant by short circuited? As if we have replaced L2 by a connecting wire. But short circuited means that we have connected across the terminals of the lamp L2 a connecting wire like this. Now the lamp L2 is in parallel with the connecting wire, and we know that according to law of uniqueness of voltages they have the same volt, and we know that the voltage across a wire is 0, so the voltage across the lamp L2 is 0. So in number 1.3.1 they are telling me give the value. So here we have done a changement in the electric circuit, so everything will change. Now in 3.1, so this is 3, this is 3.1, so this is the short circuiting. Now they are telling me give the value of U prime 2 across the terminals of L2 justify. So U prime 2 is equal to 0, and the reason can be simply be short circuited. Now in 3.2, deduce the value of the voltage U prime 1 across the terminals of L1. And by deduce it means that we need to test the previous part. So now, because L1 is the only electric component of the circuit, so UAB is equal to 24, this can be justified either by the law of uniqueness of voltages or the law of addition. So on the left we write the voltage of the battery, which is given by UPN, and on the other side we'll go across different electric components, making sure that we need to determine the voltage U prime 1, which is the voltage UAB, and which is denoted by U prime 1, corresponding for the new configuration under which we have short-circuited the lamp L2. So UPN is equal to UPA plus UAB plus UBC plus UCN, and we are interested in determining the value of UAB. So this is 24, this is 0, plus UAB kept as an unknown, plus 0, plus 0. So UCN justified previously why it is 0, as well as UPA, and this UBC has been justified because U prime 2 is equal to 0. Now U prime 2 is this voltage, okay? Now in this case UAB is equal to 12 volts. Sorry, 24. So we have determined the voltage U prime 1, which is equal to the new voltage UAB, which is equal to 24 volts. And the value of the current through the circuit. So how come we need to determine the current, knowing that we have determined the voltage. Now the lamp UAB, the lamp across the terminals A and B is not functioning anymore because 24 volts compared to 12 volts, they are not equal, so we cannot use the current, which is 0.6 amperes. One can determine the value of the current from the voltage using Ohm's law, because we know that the lamp L1 is considered as a resistance of resistance 20 ohms. So apply Ohm's law to L1, which is given by U is equal to R multiplied by I, and we are interested in determining the value of I. Putting our hand over I, then I prime, so the current is denoted by I prime, is equal to U 1 prime divided by the value of R1, which is equal to 24 divided by 20. Plugging this on the calculator, then the value of I prime is given 1.2 amperes. So I prime is equal to 1.2 amperes. And the trick in solving such type of exercises, as we have explained previously, to write the applied voltage here, which is 24 volts, and the value of the traverse current, which is given by 1.2 amperes. So now before we proceed, always whenever we have a current, we need to compare it with the rated current of the fuse. So the rated current of the fuse is given by 0.65 amperes, and the traverse current is given by 1.22 amperes. Then in this case, this may yield to an open circuit. Now let's continue the problem. Now in 3.3, they are telling us or asking us L1 may burn out Y. They are discussing again the functioning of the lamp, and the functioning of the lamp can be always described by comparing the rated to the traverse and to the applied, or the applied and the traverse to the rated. So notice that in this case 24 volts is greater than the rated voltage. So since the applied voltage is greater than the rated voltage of the lamp L1, and between brackets because 24 volts is greater than 12 volts, then the lamp L1 may burn out. We know that the lamp L1 may burn out or function strongly, but since they are telling us it will burn out, so we will say it will burn out. Then the lamp L1 may burn out. Now in 3.4 they are telling us, so may refers to the probability of the lamp L1 that it will burn out. Now the fact that L1 doesn't burn out, it will be off explained, and this usually happens because due to the presence of the fuse in the electric circuit. Now let me also mention that the response of the fuse is much faster than the response of the lamp. So although the lamp, it may burn out, and at the same time we need to consider that the fuse will cut off the circuit, and this cutting off is due to the response of the fuse is much faster than the burning out of the lamp. Okay, so as soon as the lamp starts to function strongly due to the high applied voltage compared to the rated voltage, at that time the fuse will respond much faster. The response of the fuse will be much faster, and it will cut off the circuit directly. So let's say, since the traverse current is greater than the rated current of the fuse, and this is because 1.2 amperes is greater than 0.65 amperes. Then the fuse will melt cut off the circuit which means it will be an open circuit, and protects, stops the current, and protects other electric components. Then L1 doesn't burn out. It will be off. Okay, so this is the role of the fuse. Then that's it for me in this video, guys, and the next part 4, will complete solving exercises on this chapter.